Hello again. Welcome back to Game Framework 2D. Now let's take a look at the code and how this is organized. Now this project, which does nothing more than show a background and an animated spinning mouse, and it gives us some text output, is provided here. As I mentioned in the game engine architecture overview video, this is meant to give you a template to how to build out a game engine. This is not a fully functioning game engine, nor is it intended to be. The code begins in game.c in int main. If you've done any Windows programming in the past, you might be asking yourself, wait, where's WinMain? And that's the cool thing about SDL, is that it forces Windows application development back into standards. So the standard by ASCII is that the beginning of a C and C++ program should be int main. And it provides the parameters int argc, which is the number of arguments that have been sent to this program, and a char star argv array. This is an array of pointers to character data. Cool note, the minimum number of arguments we're going to get is not 0, it's 1. The 0th, or the first argument in this array, is always the name of the program itself. So in Linux over here, this would have been gf2d. In Windows, it would be gf2d.exe. If you want to have additional command line arguments, you can just iterate through the list. So for I equals 1, well, I less than arg count, I++, and then check to see what these are and string compare them. And you pull out all kinds of command line arguments. Later on, when we work on a content editor for your project, that might be a command line option. Make it all off the same code base. As I just mentioned in the previous video with resource managers and game engine initialization, the first thing we do is initialize the system. Well, actually, the first thing we do is declare some variables. Just a note on ANSI standard C. It is in C, you are supposed to declare all your variables at the beginning of a function block. This is how it is organized when it is compiled, and this is how they expect you to write the code. Modern compilers, and I think even some of the recent specs, have relaxed that requirement, but I try to work with a strict style. My adage of when you're a C programmer, with the great power you get, you must have great responsibility. So I try to exhibit discipline when I'm writing C code to keep from making a lot of mistakes that can happen when you have sloppy coding. Now, if you're talking about C++, declaring variables at the beginning of the program block does not always make sense, since when you declare the variable is in the code is when its constructor gets invoked, and depending on if you put it in a subscope is when its destructor will get invoked. So where you put a variable in C++ has more context than in C. So I just try to give myself one-stop shopping when I see a variable in my code. I know to look at the beginning of the function, and if it's not declared there, and if it's not declared in the parameters, then it's probably coming from some sort of global state. So it makes tracking down where ever my variables are a little bit easier, a little bit cleaner than having to rely on tag systems and right-clicking and going to definition of. Anyway, moving on. So the beginning of any function, you have your variable declarations. Then we have the program initialization. So the first thing we initialize, the thing with no dependencies at all, is our logger. And it's going to write to gf2d.log. And this last flag here is whether it should be in append mode or overwrite mode. The default is overwrite mode. It means every time I run the program, it's going to overwrite the previous log. If I want to keep the logs around because I'm trying to see some differences between different runs of the game, different states of the game, different variables I might be testing, I can keep them alive by adding the one flag. But I warn you that in a long time ago, that used to be the default behavior, and I would just manually delete the file every so often. You can fill up your file system if a log goes a little crazy. So that's why it's in default overwrite mode, but you can go to append mode. And if you want to look at that file, right there in the source of the file, you'll see gf2d.log. And look, it's the same stuff that was echoed out here. Less new lines, I guess. All right, moving on. Now we're going to log. So my slog is based on the printf style. I can have variable arguments in here, and you'll see at some points throughout the code where I will, I can say add a %s here, and I can add a string. So this is a tokenization of this string, and it will automatically populate the %s with, say, argv sub 0. As I already said, the 0th argument in this list is the name of the program. And I could even go down here and I could do the same thing, %s, and I could do comma argv sub 0. If you're new to C, you might say, oh, cool, C allows you to have a variable number of parameters in your functions. No, actually, that's not true. It is pretty much only when we're dealing with the variable argument system, which is meant to be used with this string population system. Everything else has a very specific and strict number of arguments. Let me see what that looks like. I'm going to go over. I'm in Linux right now, so for those of you in Windows, you would hit build and then run it. I need to hit make and then /. And oh, look, it began. Oh, look, it even includes the // for how the whole program was run. So there's an example of the slog in action. Another important feature is that it gives you file and line number where that comment was made. So it really will help with debugging. And just so you know, the simple logger is its own standalone GitHub project that you can include in any C or C++ project if you so desire. It has no dependencies other than the standard C library. Okay, moving on. We are slogged. Now we initialize the graphic system. I will go into greater detail of what's going on in this at a future time, but this is the name of the window, the screen resolution, the rendering resolution, which doesn't have to be the same thing, the default background color, which in this case is passed as a 4-dimensional vector with 0 red, 0 green, 0 blue, and 255 as the opacity. The alpha value is 255, so it is opaque and black. And this last flag, if I remember correctly, is whether we're in windowed mode or full screen. 0 is windowed mode. Sometimes the full screen has some issues if the resolution that you're asking for isn't available. So we start in windowed mode. Something to consider if you want to use this code base going forward is writing a system that is a bit more robust to account for different resolutions that you actually have. SDL provides those capabilities. I just never implemented that code for this sample project. We set a frame delay. So if we want to keep a steady 30 frames per second or 60 frames a second or 10 frames a second, if you want to like have about a 7 frame per second update, we can compile that and see what that would look like. Because you can see the mouse is now spinning about twice as fast as it was before. It's actually like 15 and change would be about 30 frames a second, and 7 and a bit is about 60 frames a second. Since I'm working in a 2D game, I don't really need high frame rate. So 15 is a fine frame rate. This is an unsigned 32-bit integer. It's the number of milliseconds to delay between frames. And down, skip ahead, so initialize the sprite system, disable the cursor, the system cursor when we're over the screen, loading up default background and mouse, and now we have the main game loop. So while not done, this is that big loop of updating and drawing. So everything we want to update, so right now we're calling SDL pump events, which SDL is our library that we're using for a wide variety of things, and one of them is user input. So it is updating its internal state for all the input things that it is currently tracking, which defaults pretty much to keyboard and mouse. If you have a touchpad, that's an option too. In the future, you might want to work with like adding an Xbox or PlayStation controller over USB, and you can just, if your system recognizes it as a game controller, you can use it as a joystick in SDL. But pump events updates all of SDL's internal structures, and then here's now where I get the current keyboard state, which I use down here, and I check to see if the escape key has been hit, and if so, we set our done flag to 1, and we exit the game. But other updates are we get the mouse state, which gives us the mouse position in X and Y. These are, it's passed by pointer, this function. So get mouse state will return the button mask, more on what that means later. And if you provide it the address of an integer and an address of another integer, it'll populate that with the current mouse X and Y position in screen coordinates. And that's where we use to draw the mouse. So here's the draw sprite. So this is one of the utilization functions that I was talking about for the resource managers. So draw image, draw sprite. The sprite draw function has the pointer to the sprite to draw, where to draw it. We have scaling, we have positioning, we have, well, this is position. Scaling, rotation centers, scaling centers. Color offset. So right now there's actually a color offset. That's not the default color of the mouse. Mouse color was set up here to be, well, that pinkish color. And then we call next frame. This last function will render the current frame and wait to make sure we have waited the 15 milliseconds, depending on how much work is going on up between last frame and this frame. All the updates and the draw may have taken 12 milliseconds. And if that's the case, it's going to wait the remainder 3 before going to the next frame. This will make sure that we have a steady frame rate. However, if we do too much work, it'll just go as fast as it can. You can see here all the image loading is relative to the root of the project. So there is an images folder in here. We have the images folder, and inside the images folder is the backgrounds folder where we have bgflat.png, and in the images folder we have the pointer. Backgrounds and pointer. And I give you a couple other random sprites that there's a space bug and a mech that you might find useful as a little proof of concept project. Placeholder graphics, if you will. If you'd like, we can even output our current FPS. And you can see we're running at 66 frames a second. It doesn't work out perfectly because of SDL subsystems, but you can see every now and then we drop a frame, but it's so infrequent it doesn't matter. Oh wait, that's the 15 frames a second. I may have lied. If we want it slower, there we are at 33, so we can probably even go a little bit more than 33. Now I'm intrigued. All right, about 33 gets us about 30 frames a second. Since we're only at millisecond precision with the delay, we can't make it exact, but we can get it pretty close to several decimal places. All right. Let me go into one more bit here. Let's take a look at the sprite system. So if you go to the sprite.h, and this is a good segue into how you should structure header files in C and C++. You'll notice the first thing are some compiler directives. If it starts with the hash symbol, the pound symbol, the sharp, then it is a compiler directive. It's technically not C. It is technically code that is interpreted by the compiler as commands for the compiler. And with the compiler, we can set up some state. So in this case, we're checking to see if there's a state yet for the identifier underscore gf2d sprite h underscore underscore. And if it's not set, so this is if not defined, then we shall define it. And this if block is ended at the end of the file down here, end if. So everything between here and the last line of the file is omitted if we've included this file before. And the reason that is because this sprite file is going to be included by game.c, sprite.c, and probably draw.c, and however many other entity.cs that we work with. So I don't need, when I'm linking this all together, to have multiple copies of this header file in every single file that ever included it. One is enough. And that's what these include guards are meant for. Now you might think, what, can't the compiler just figure that out? Well, yes, it could in theory. But as with many things when we're dealing with C and C++, the philosophy behind it is let the programmer decide. Maybe there's a use case that someone can envision where I want multiple copies of the header file in my code base. This gives them the option. I can't recommend it. I can't think of a case where that would be necessary or right, but it's an option. Now let's talk about the includes. You're probably familiar with includes from other languages. Everything needs to be able to import additional code so I don't have to have copies of it everywhere. Of course, this is even a header file, so already on that bandwagon here. You'll notice there's two different styles here. There's the include with the greater than less than brackets and includes with the quotes. They are functionally the same. They will include that header file and its contents when this file is compiled, as long as the its include guards are honored. The difference is the ones in brackets are meant to be system level libraries, ones that don't update very often. So when we compile this, the compiler is going to check the header files to see, hey, has GFC types been modified since the last time we compiled? And if so, I'll need to recompile this file. It skips that check for the ones in the brackets because this is a system file. This never updates. So we're going to skip worrying about if we need to recompile that or not. Now, with that said, you want to organize the order of your includes from the most stable, the most mature, the least likely to change, to the most volatile, the thing that is most likely going to change between over the life of this project. In this case, I'm making a header file, so I am my own most volatile, but I'm including all of the core libraries, the GFC stuff that I need here. I don't include things that I don't need. I see there are some lazy programmers out there that will make a single include file that includes everything that they think they will possibly ever need, and so they don't have to think about it. But think about it. If I'm using a library that has a lot of edge cases and features that I might not need, I don't want them included when I compile. Also, order sometimes matters in ways that is hard to anticipate, so just always go by the minimum set of includes you need at any given point in time. This header file needs to know SDL commands because we have some SDL words. The uint32 variable here is not a standard C. This is provided by SDL, as well as sint for a signed 32-bit int, and unsigned and signed 16 and 8-bit, and floating point. It can be a signed and unsigned floating point, and whatever the bits are. It provides a whole bunch of them to make them a bit more cross-compatible, because there have been some standards proposed over the years, but not every operating system has honored those. SDL forces the point. We also need to know SDL texture. So this is an SDL. This is an SDL identifier. Text line is one I wrote in my GFC text. And we're going to do a lot of stuff with the vectors, and I wrote a vector library myself that's in GFC. So these are all the necessary and no more from most stable to least stable includes. Now, something else you'll notice is what we are doing here in the header file. There's a lot of comments here. I am using the Doxygen style or JavaDocs style commenting guides. What that means is that whenever I make a function prototype, which is one of these, a forward declaration of a function, what I will do here in my header file is I will describe what that function is supposed to do, what its parameters are, and what it's supposed to return when it's complete. The idea behind that is that this becomes the table of contents for the library file that I'm writing here. So for sprite.c, which has a whole lot of the actual code and not a lot of comments, the header file has the table of contents for what I need that I will find in the C file. But if I want to work with this library, this gives me all the information I would need in order to work with this library. What does the function do? Sometimes there's some additional notes to worry about. Some parameters might be optional. And by the way, optional when I have a pointer means I pass null. I don't skip the parameter. So it's a nice, makes it your code easier to read. And if you see someone talking about self-documenting code, that's what this means, is because you can actually run this through a doc generator and it will read these and interpret them. That's why they're all like tagged with the @brief, @param, @returns. And it can generate document pages. That's what self-documenting code means. It doesn't mean I write so clear that you don't even need documentation. That's garbage. We mean you write code that can produce its own documents. It's also a great hint to your future self when you're starting to write something. You can write a whole bunch of functions that you think you're going to need, and then at a later date come back and write them. Like, oh wait, what was I supposed to do with this function? Oh right, I needed to do that. That's what this parameter does. That's what it returns. So it's also a note to your future self when you're either continuing to write this library or using it. So the first thing after the includes is this type def struct. If you remember when we were talking about the Quake code base, it followed a similar model. It would define a structure, it would define a type based on that structure. This does it all in one block. We've type defined struct sprite. So this is the type that has been defined. It has been defined as struct sprite _s. And the reason why I do this is because if I need to self-reference, the sprite identifier doesn't exist yet. It doesn't exist until line 18, and compiling is done in order. But if I needed to have, say, a child sprite, so I could do, I hate typing, so I will copy and paste a child sprite. I have a pointer to a structure. Now, at this point, that becomes synonymous with the word sprite. So that's how I can self-include. I'm not doing that, though. Just giving you an example. We'll do that more when we start making our own entities. So that's what a header file, in my professional opinion, is for. You define types. You define function prototypes. You do not actually make the functions. You do not work with the types you've defined. You just create the language, the blueprint, the interface for the library. It is within the C file that the actual work goes. So we're defining the types that everyone who includes this file knows what a sprite looks like, and all of these functions that work with the sprite. Now, there is a rule of thumb in C and C++ that every class gets its own pair of source and header files. I am following that with this architecture, but I am following that in C. But wait, professor, we're working in C. There are no classes. Yes and no. C has no formal class system, no formal class structure. However, a class and object-oriented programming is a methodology. You can accomplish that in C, because what is a class except a set of data and the functions that operate on that data? All I'm doing is that without the formal structure of the class. And let me tell you, as a long-term C and C++ programmer, when I'm programming in C, there are many, many times where I miss having some of the features of a constructor and destructor handling auto cleanup and auto initialization and copy constructors. There are times where I miss that because my code can get a bit more verbose, but There is nothing stopping us from doing that same methodology in C. Which leads me to a bit of an aside. Why am I doing this in C anyway? I mentioned this in a previous lecture when I was talking about SDL, but I'm going to mention it one more time here. C is functional. It's foundational. It is about as close to the metal we can get without jumping into assembly, and assembly is an option when we're programming in C. I just, avoid that like the plague. Things you write in C, since they don't have any modern bells or whistles, are very easy to include in other languages. It naturally goes into C++, but the way C++ handled its class system is not the same way that Python handles its class system. It's not the same way that Java handles its class system. But functional programming, when you've created the code that just has parameters and return types and it's flat, it just much easier to interpret, and most languages can just load a C library and use it. In fact, a lot of languages, a lot of your scripting languages like PHP and Python are written in C. So that's why I'm working in C. Are you going to work in C in the professional world? No. No, very likely no. Unless you're working as an embedded systems programmer or a very low-level programmer like NVIDIA or AMD or Intel, you are probably not going to work in C. You're probably going to work in C++ if you're working in the games industry, or C# if Unity sticks around for any while. But it is mostly C++, which is why even when I'm working in C, I'm going to be telling you about how things are done in C++. Which is why if you've taken my game mod programming course, we start with Quake 4, which was done in C++. It's important to know. But the cool thing about this is that if you want to promote your project to C++, or at some point you decide you want to use a library that's a C++ library, you can, and it works together really nicely. All right, one more thing. Let's start taking a look at how this code actually works. So as I mentioned in the game engine architecture overview, this is a resource manager. This is the resource that we're managing. We're managing sprites. We have a reference count because this is a shared resource. More than one thing can share the same sprite. I keep the text path of the file name in the file path, where I can find the file. I use this because whenever I ask for when I want to load an image or a sprite, I'm going to check to see if I already have it in memory. So I'm going to go through the list of things I've loaded, and if I have it, all I'm going to do is increase the reference count and return a pointer to that. I'm then going to load up the resource and keep all the information I need about the sprite. This is the manager initializer. This lets us load an image. So because sprites are based on images, in fact, they're based on sprite sheets. So if I go into Game Framework 2D, I go to my images, and I open up my pointer here. Let's full screen this and zoom in a bit. This is a sprite sheet. It is a flat image with some transparency. It is a uniform sprite sheet, which means every frame is uniformly spaced. In this case, there are 16 cells or 16 frames on each line. And in theory, I could have more than one line. Let me show you a larger one, my ED210 image right here. This one is way more involved. So this one is also, if I remember correctly, I made this 16 frames across and as many frames, many rows down as I need to fill in all the sprites. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, almost 10. So there's almost 160 frames of animation here. No, the last one's the wrong image. I can access this by frame number since I have since I know how many pixels are wide and how many pixels tall this is. And I know there's 16 pixels per line, I can say access frame 24 and know exactly where that should be on the sprite sheet, and I can copy and paste that. Since my sprites are a bit more involved, I need to be able to access it on a frame, and I had to draw them to the screen. It's already doing all the work that I would do if I had a flat image, like the background image. So I go to my background, This background image is just a flat image, or you can consider it a sprite sheet with only one frame. So I made my sprite system pull double duty in the code base. So the frames per line might be 1, and the frame width and height might just match the texture and the surface width and height. Anyway, let's take a look at what the C code looks like. And I'm going to wrap this up shortly. So here is my sprite manager. So I make the sprite available to the world. Anyone who wants to include the sprite system will know what a sprite looks like. But the sprite manager is local to this file. Now, something else about the sprite manager, it is a singleton. I'm only ever going to need one sprite manager. I'm not going to need multiple. The sprite manager is going to provide sprites that are individually a shared resource. I will, be able to provide multiple references to the same sprite image. I've decided to define this new type as my sprite manager. I keep track of how many I have, and I have a pointer to the list. This is going to be my resource pool. During initialization, however many I want with a max here, making sure I have at least a value. I can't do 0. Let me make sure it's unsigned because I also can't do negative. I will allocate that many sprites, and I'll keep that memory address here, which I can then index into as an array. I also memset the whole thing to 0 because one of the important things to keep track of is my reference count, and as long as that's 0, that means that spot my memory address can be reused. I make sure that I have the subsystem initialized with PNGs. If you want to make sure you also have JPEGs, you can do a bitwise or with the init JPEG flag as well. And now here's the fun part I want to really showcase before I end this, is at exit. This is a function that will queue up a function to be called when the program exits. It takes the name of a function. It does not take the function being called. So for instance, at exit, image quit is the opposite of image init. Whatever I have initialized, I will deinitialize. And now that I am initializing my sprite system, I'm going to close my sprite system. So I make sure that the cool thing about exit is that it calls them in reverse order. So the most recent thing that's been queued up for at exit will be the first thing called at exit. And the first thing that is called at exit will be the last thing that actually gets called when the program exits. So this function, by the way, so this is the function. It is not being called. It is the name of the function. This is giving us the function address, not calling the function. This will do all the necessary cleanup automatically, which is why we initialize the sprite system here, but we don't have to deinitialize it explicitly. It's already being handled once this return 0 is called and the program exits when main is complete. All right, I think that's all the time I've got for this video. It's already gone a bit longer than I wanted it to. I will go into greater detail on resource managers in a future video. Hopefully I'll be able to get to that this week. All right, thanks for watching.